Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. This is for chemistry, but it could also be review for CP physics on the subject of chemistry. Once again, I put up the heating curve for any substance, reminding you that the temperature increases as you add energy to any substance. They generally begin in the solid state, and on the Kelvin scale, absolute zero, okay, 0 Kelvin, is the coldest temperature you can possibly have. Substances increase their temperature as you add energy to them up until they get to their melting point, in which case they undergo a phase change from solid to liquid. Then, as you continue to add energy, it increases and becomes higher in temperature in the liquid state until you reach its boiling point. Then it undergoes a phase change and transforms from a liquid into a gas. And then again, as you continue adding energy to it, the gas becomes hotter and hotter. All right. In a previous episode, I did some practice problems in changing the temperature or the mass, solving for one of the four variables uh, in either the solid, liquid, or gaseous state. In this episode, I thought it'd be interesting to do calculations because I love math in just transforming from one phase to another. So the temperature is not going to change. And the parameter that we're going to be looking at is the heat of fusion or the heat of vaporization. So here we go. Let's make up some practice problems with random variables. You should also practice your Greek prefixes. So a reminder that mega is 10 to the sixth power. Kilo is 1,000. Milli is 1/1000th. And before that, a centi is 1/100th. And a micro is 10 to the negative 6, 1/1 millionth of something. I'll avoid doing gigas, nanos, or picos for today, but you should be practicing these skills anyway. So let's do a energy transfer. Let's start with water, the most common example you guys are familiar with. And let's say that I have a mass of 125 grams of water. And of course, it's at 0 degrees and it's in the ice, so it's solid. And it's at 0 degrees C, so I'm only doing a horizontal change this time around. And I'm going to add, well, okay, I want to melt this. Let's do that one first. So the equation is Q is equal to M delta H of fusion. The heat energy needed to transform a substance from one phase to another is equal to the mass that we're dealing with times the heat of fusion for that particular substance. All right, so in the case of this problem, the mass would be 125 grams. And when I go to my handy dandy lookup table, your reference sheet for the substance of water, its melting point is 0 degrees. That's where I am now. Boiling point, specific heat in a solid state, specific heat in a liquid state, specific heat in a gaseous state. We don't want any of that. So almost, well, the second to the rightmost column says heat of fusion in units of joules per gram is 334. 334 joules per gram. So 334 joules per gram. And this is it. It's a very simple equation in the idea that it only has three terms in it: heat energy, mass, heat of fusion. And powering things up, 125 times 334 joules per gram means I would have to expend 41.8 kilojoules of heat energy to completely melt that quantity of ice. Okay, so there's my first example. If I want to completely melt 125 grams, which would be a cup of ice, a large cup of ice or so, it would take 41,800 joules of heat energy to completely melt it. All right, so let's do another example. This time I'm going to take a mass of 275 grams, and let's put it at copper. Okay, so the mass is copper, and this will be at its boiling point. So it's at 2,562 degrees Celsius. And let's say that I add that amount of heat energy to it. So I add 41,800 joules of heat energy to this. And the question is, what do I end up with? Okay, so here we go. I'm going to take the equation Q equals M delta H fusion, and you might be wondering, well, which one is the unknown here? Because Q is known, M is known, and delta H of fusion for copper is known. I'll write it down from the table. Oh, and I put fusion, I should put vaporization, right? Vaporization. I'm boiling this copper, not melting it. So copper at its boiling point has a heat of vaporization of 5,070 joules per gram. Okay, so if all three are known, there's something wrong with this picture. And here's what's wrong with this picture. It's not self-consistent. So I've made up three random numbers, but they don't necessarily actually equal each other if you plug them in. In fact, I'm very sure, since they're just random, that if you plug this into the equation and say, hey, is it true that 275 grams times 5,070 joules per gram is equal to 41,800 joules? I'm pretty sure the answer will be no, it's not. So what has to give? The answer is the mass. Treat the mass as an unknown variable for right now. And you're saying, but wait, it's 275 grams. Just roll with me, all right? Solve for mass for right now. Mass is equal to Q divided by the heat of vaporization for the substance. And that means I'm going to take 41,800 joules. And I'm going to divide that by 5,070 joules per gram. Some of you want me to write this out, right? So 41,800 joules divided by 5,070 joules per gram. Notice that the joules cancel and 1 divided by grams is grams. So the answer is going to be in units of grams. And my calculator says 8.24 grams. So what does that mean? It means I don't have enough heat energy to melt all of the copper. Vaporize all of the copper. 41,800 joules is only enough to vaporize 8 grams out of the 275 grams that I started with. So in the end, what I should say is 8 point, well, here's the thing. Yes, this is 3 sig figs, but here this is only to the nearest gram. So by the rules of significant digits, when you're adding or subtracting quantities, you have to round it to the least significant known digit, column, I should say. So we only know it to the nearest unit of whole grams. So this 8.24 grams that we just calculated really has to get truncated, rounded down to 8 grams. 8 grams of copper vaporized into a gas. And so now subtract those 8 grams from the 275 that I started with, and you have 267 grams of copper remain in liquid state. Okay, so this is like an old algebra problem where you only go partway through the substance. I don't know, that's a poor way of putting it, isn't it? All right, there's my first example. When I add only this much heat energy to it, it doesn't completely go all the way across on this horizontal bar. Visually, if going all the way across would do all 275 grams that I started with, I only made it this far, 8 grams out of 275. So a little bit of it vaporized, and the rest of it is still at its boiling point, but it's still in the liquid state. All right, so there's a fine example. Let's make up another example. I have mystery substance X once again. And this time for substance X at its freezing point, which is the same as its melting point, I measure that I expend an energy of 5,280 joules. You might recognize the number as being the number of feet in a mile, but there you go, some random number. And the mass that I successfully freeze in this case, so I'm removing this much heat energy. The mass that is converted from liquid to solid state happens to be, let's see, 39.4 grams. I was trying to think of how many inches are in a meter, something like that. Okay, so there's my two randomly generated numbers, and the only unknown is from the equation Q is equal to M delta H of fusion, heat of fusion. So I'm solving for the heat of fusion this time, and I end up with, when I take negative 5,280 joules, and I divide that by 39.4 grams, and by the way, this is joules per gram, but I have the right units or I'm going to be in big trouble. So 5,280 divided by 39.4, and I end up with a heat of fusion of 134 joules per gram. Now, you're wondering what I do with that minus sign. So when I go from liquid to solid, I'm removing heat energy. When I go from solid to liquid, I'm adding heat energy. And the heat of fusion is a constant no matter which direction you're going. So they're listed as positive values here. When I'm melting it, I'm adding heat energy. When I'm freezing it, I'm removing heat energy. And this just lets us calculate the quantity of heat energy necessary to change phase. So I'm dropping the minus sign, essentially, is what I'm explaining to you, that yes, I had to remove the heat because I was going from liquid to solid, but as far as calculating the heat of fusion, it's a positive number. And I'm curious, so randomly, did I happen to pick any substance that has a heat of fusion somewhere close to this random number? So in this column, I'm looking for anything that's really close to 134, and there's nothing that close to it. I would say the closest number I'm seeing seems to be 109. So maybe this was ethanol that I was dealing with. It's the closest on this list of 12 to this, substance X. So maybe substance X was ethanol, but poorly measured. All right. So in my previous episode, I made up these practice problems and then gave you, a chance to work them out yourself. There's more I want to do mathematically, but I'm going to try to just keep this short. Try. And maybe just give you some practice problems right now with what I've just done. So there's really the equation for this part, if you don't look at your reference sheet, says Q equals M heat of fusion. And for this part, Q is equal to M heat of vaporization. Those are the two equations to use. And there's only three variables. And I've modeled for you that you might not make it all the way across from one phase to another. You can end up with a mixture, just like you can have a cup that begins as pure ice, and as time goes forward, it melts, but not all of it instantly. First, some ice melts and you have a little bit of water. With more time and energy, more the ice transforms into liquid water, right? So an ice cube or a cup of ice melting is a process of going from 100% ice and 0% water to 50-50 to eventually 100% water and 0% ice. So that was what was going on with this example with the vaporizing copper and ending up with just 8 grams of it vaporizing and the rest of it still in the liquid state. So let's make up some practice problems for you to demonstrate your mastery and love of math. So here we go. Practice problem 1. Let's say I guess I'll just go up the list this time. Whatever it is I have information on. So I did water, did silver other episode. Let's do methanol. So I have 10 point, I have a mass of 10.8 grams of liquid methanol. All right, that's what I'm starting with, a mass of 10.8 grams of liquid methanol. And I want to transform all of it into the solid state. So freeze all of it and tell me how much heat energy do I have to remove to freeze it. And it seems like I could just zoom in a little bit more for you students. Okay, so I have 10.8 grams of liquid methanol. Calculate, please, how much heat energy would I have to remove in order to freeze all of it? All right, let's do another one. Practice problem 2. Just going up the list. I have iron, and by the way, if you don't have your reference table handy, I guess I should look it up for you. Liquid methanol has a heat of fusion of 99.0 joules per gram. Although you should have your reference sheet and you should have looked that up already. So the heat of fusion for methanol is 99.0 joules per gram. Next one, I have some lead. And I take amount of heat energy of, let's say 3,210 joules, and I apply that to a quantity of solid iron, which was at initial temperature of its melting point, so 1,500 38 degrees C, it all melts. And of course, you looked it up. The heat of fusion for iron is 266 joules per gram. So calculate, please. What would be the mass of the iron that I just melted? All right, number 3. I have ammonia. All right, and for this ammonia, by the way, as chemistry students, you should memorize the formula for ammonia is NH3. Ammonium polyatomic ion is NH4 with a +1 charge. Ammonia is a neutral molecule. NH3's formula. Just memorize it like water is H2O. And with this ammonia, I'm going to vaporize it. Let's do this. I have a mass of 860 grams of the stuff, and it's at a temperature of its boiling point, which is negative 33 degrees Celsius, and it's liquid. So I have this liquid ammonia, and it's all at its boiling point, but it's still liquid. And I add a heat energy in the amount of, I suppose 2,000 joules. Oh, 2019 joules, right? Time to take care of the juniors. Sorry, the people who graduated last year. So 2019, the beginning of the school year. There you go. 2019 joules. So tell me, how much mass melted? M in the liquid state, not melted, vaporized, and M in the gaseous state. So you're starting with 860 grams. You're presumably going to vaporize some of it. So some of it becomes a gas, and what's left behind is a liquid, and these two added together should add up to 860 grams. I'm assuming, of course, that I'm giving you less energy than it takes to vaporize all of this stuff. Now, eventually, I'm going to make a mistake on that, right? And I'm going to give you so much energy that all of it's going to vaporize. And then the question becomes, well, then what? What happens next? So let's make that a future episode where we practice that math calculation as well. Okay, so here's 3 of them. And then the 4th one, just because, it's fun to have substance X. So now I have substance Y. And it happens, I don't know if it's in a solid or liquid state. All I can tell you is that when I have a mass of 412, I haven't been practicing Greek prefixes, have I? Let's call them grams. So 412 was quitting time in my aerospace job. When I have a mass of 412 grams and I apply heat energy in the amount of, I actually had a random number generator going the other day. So let's make it in the thousands, right? So 1,976 There you go. Joules, it changes state. So I'm going to be very open on this one and say, I'm not even going to tell you if it goes from between solid and liquid or if it goes between liquid and gas. And my challenge for you is calculate the heat of whatever it is, vape or fusion, and then make an attempt to identify what could it be if you had free choices off of either of the last two columns on this reference table. Which one comes closest to this particular delta H? So this is really just a math exercise, not something that I pulled out of a laboratory, right? All right, so pause your tape. I'm going to pause recording. I'm going to do my calculations. You're going to do your calculations, and then hit play and let's see how you did. So here's the four problems again. Number one, I have 10.8 grams of liquid methanol. I want to freeze all of it. The heat of fusion is 99.0 joules per gram. How much heat energy do I have to remove? Number two, I have 3,210 joules of heat energy. I apply it to solid iron that's at its boiling melting point, 1538 degrees Celsius. If all of it melts, given that the heat of fusion for iron is 266 joules per gram, what was the mass of the iron? Number three, I have boiling liquid ammonia, 860 grams of it. I add 2019 joules of heat energy to it. How much of it ends up as liquid? How much of it ends up as gas? Assuming, of course, that not all of it becomes a gas. And number four, I have some strange substance Y. The only two things I was told was I had a mass of 412 grams. I apply heat energy of 1976 joules, and as a result, it changes state. Not even told, is it solid to liquid, liquid to gas? I don't know. I was just told it changes state. Calculate what is its heat of whatever it is, and which out of the last two columns is the number that comes closest to this result. All right, pause, calculate. Hopefully you paused it. Here we go. My results. For practice problem one, I got 1.07 kilojoules of heat energy. Number two, I got 12.1 grams. For number three, I realized if you didn't have your reference table, shame on you. I forgot to tell you that the heat of vaporization for ammonia is 1,360 joules per gram. And as a result, I get 1.5 grams, so rounded to the nearest gram. 1 gram of it becomes gas, and the other 859 grams of it remains in the liquid state. And number four, the heat of vaporization works out to 4.80 joules per gram, which is much smaller than any number on the table. The lowest number on those two columns is acetone, and this is far, far below acetone. So probably not acetone, although that's the closest value to it. All right, that concludes this little session. There's lots of math that could be done here, and you should embrace it, challenge yourself with some questions. I'm sure somewhere online there's a calculator that can verify the results of your calculations. Ciao.